Okay, let's look at some ways in which we can do chi-square analysis in Minitab. So, chi-square analysis is for data that are not continuous, that we can't measure on a continuous measuring scale, but that are data that instead fit into discrete categories. Okay? A really good example of that is things like binary data, where there's only two possible states, on or off, up or down, left or right. Very, very straightforward. Other examples might be the number of people who have different colored hair. We might have, out of a sample of 1,000 people, we might have 200 people with black hair, 200 people with blonde hair, 600 people with brown hair, and so we can easily put them into those, or maybe not easily, but at least we can try to put them into those discrete categories, because hair color is not something you can easily measure on a continuous scale. Another example might be coin tosses. Toss a coin 100 times, you would expect to get about 50 heads and 50 tails, and that's two possible outcomes, two discrete categories. So these kind of data we would have to analyze with tests that are suitable for categorical data. And one of those types of tests are chi-square tests. Chi-square tests work on data that fit into categories where we have a certain number of observations for each individual category. Okay? A good example, again, would be, something like a coin toss. And we'll use that as an example for how to test things in Minitab to do with categorical data. So let's say, for example, we've done a coin toss. So coin toss, let's put that over here. So again, the label for this column I'm going to put into the gray box, the gray cell, the gray row, so it doesn't turn our column here into a text column. Now I am going to make a little table here in Minitab to help me understand what data I'm dealing with. So when I do a coin toss, I might get heads, I might get tails. Okay? So let's say for example I've tossed the coin 100 times. I got 72 heads and 28 tails. Okay? Now let's think about this for a second. I've got 72 heads, 28 tails. Is that a number of heads and tails that you would expect based on what you know about how a coin should behave when someone tosses it? You might look at those numbers and think, well, that's a lot of heads to toss in 100 coin tosses. Are you really that lucky? Are you really that, or is that really something that would happen by accident, by random chance, or were you using a loaded coin where you knew you'd get that many heads? Well, we can test that. We can test that by using a test called a chi-squared goodness of fit test. A chi-squared goodness of fit test will take an observed outcome of an experiment, say for example here the number of heads and tails in a coin toss, and compare it to an expected outcome of an experiment. What we would expect to see if this behaved randomly, for example. So what would the expected outcome be for 100 coin tosses? Well, you'd expect each of the two outcomes, heads or tails, to come up an equal amount of time, so about 50-50, right? 50 for each. Well, let's see if we can test that using a chi-square test. In Minitab, if you go to your stat menu and you go to the tables option, tables in the stat menu, because we're dealing with a table here, right, in our spreadsheet, you can go down and you can find a chi-square goodness of fit test, one variable, chi-square goodness of fit test. Now, what Minitab is asking me in this window is, what are your observed counts? How many things did you observe happening in each category? Well, my observed counts are in my column number 2, my coin toss results. So I can double click that and it'll make that my observed counts. Now, the test it asking me to apply is, I have a range of options. I could say equal proportions, specific proportions, or proportions specified by historical counts. These will all do the same thing, but using different reference points for Minitab. Now in this case, the easiest option is just to use equal proportions, because we've just discussed I would expect to find equal proportions of heads and tails in my coin toss, right? So I should test my actual observed outcome against those equal proportions. So let's just do that. Let's leave that option selected. Let's click OK, and Minitab will produce some graphs which are interesting if you want to have a look at them. But they're not important in terms of the actual test result, because if you look at your output window, you will find a chi-square goodness of fit test result. And you'll see down here, we have a p-value for this, and a chi-squared value, and the degrees of freedom, and the n, the number of observations we had. So, in this case, the p-value, it says, is 0.000. Now, it's very important in Minitab to understand that that doesn't mean the p-value is literally 0. The p-value can actually not ever become 0. It's impossible. So why does it say 000? That's because Minitab is lazy. Minitab stops reporting decimal points after 3 decimal points. So this p-value could be, for example, 0.000000002, or it could be 0.00000000056. Who knows? We don't know. All we know, it's less than 0.001. So that's how you would express this kind of p-value. The p-value here is less than 0.001. Is that less than our critical p-value of 0.05? It certainly is. So that means we reject the null hypothesis, and the null hypothesis in this case for this test is there is no difference between the observed and expected coin toss results. So we reject that because of our p-value, and we conclude there is a difference between the observed and expected outcomes. We're saying I was unusually lucky to get 72 heads. Okay, that is very unlikely to happen by random chance. So we can assume I was cheating. We can assume I was using a loaded coin or something else was going on. Okay, so that's how a chi-square goodness of fit test works for something where there's 2 possible outcome categories, heads or tails. But how would this work if we had more than 2 possible outcome categories? Let's say we've got a dice we've rolled. Okay. So we've got 6 different outcomes. We can roll a 1, a 2, a 3, a 4, a 5, or a 6 with our dice. And we'll call it a dice roll. Now, if I roll the dice 600 times, let's say we've done 600 dice rolls, and I got 200, or let's say I got 61s, 62s, 63s, let's say 100 threes, 140 fours, and 100 fives, and that would leave me with 200, 300, 460, 140 sixes. Okay? Let's say I got that result. Would that match my expectations? What would I expect to find in this situation? Well, I would expect to find, again, an equal distribution across those 6 categories. I would expect to find about 100 rolls for each of those numbers. So let's go back to our tables and chi-square goodness of fit test. And let's see if I change this to my dice roll and leave the equal proportions, is that what I would expect to find? Is the test going to tell me that I got the expected result? And again, look here, the p-value is less than 0.001. So again, there is something dodgy going on with that dice I was using, with those dice, the die I was using. The results do not match my expectations. Okay. Now, let's look at an example where we would not expect to get even results. Okay. Let's say, for example, there's a let's say, for example, I would check in a population of insects, right? So insect gender, and I've checked how many males and females there are in this insect population. Now, in the males and the females, let's say I have 1,245 males and 1,672 females. Okay. But let's say that's a sample I've recorded out in the field. I've collected a certain insect species and checked how many males there are and how many females there are. But let's say, for example, my expected outcome here would have been, based on literature that I've read and how these species behave, I would have only expected 23% of the insects to be males. So let's say this should be 0.23, right? Percentage expressed as a decimal is 0.23. And the female would therefore be expected to be, proportion would be 0.77, okay? So now I don't have even, I don't expect to get an even outcome. or the same number of responses for each category, but I have at least some idea of what I was expecting, right? 23% males, 77% females, and I've put that into my little spreadsheet here. Now, how would we test a goodness of fit test with these kind of expected outcomes? Well, I go into stat, tables, and then a chi-square goodness of fit test again. My observed counts this time are my insect gender counts, but this time I don't want to test against equal proportions because these are not equal, 0.23 and 0.77. I want to test against specific proportions that I've specified myself. So when I click on that, you'll see a little box opens up here on the right, and it's asking me, well, which specific proportions do you want me to use? And I tell it the ones that are in the expected proportions column. Click OK. Again, it produces these different graphs that are not so interesting to us at the moment. And I get another chi-square test with a chi-squared value and a p-value. And again, in this case, the p-value is 0.00 or less than 0.001. So a highly significant difference between the observed outcome and the expected outcome. In what way is it different? Well, hopefully it's fairly obvious that I get way more males than I would have expected based on the literature I've read. Why could that be? Well, that's interesting. As a scientist, I might want to investigate that. Is there something going on in this habitat where a lot of females are being eaten by predators? And that skews the expected sex, the ratio of the gender ratio from the expected values. Or is it maybe that there's a disease that's affecting the females more than it's affecting the males in this population? So you can see how you could use that in a research context. Okay, that's the chi-square goodness of fit test. That's when I have categorical data and I know what outcome I would expect. But let's say, for example, I want to compare categorical data across different samples or different populations, for example. Let's say, for example, there's another population. I've measured insect gender in two different populations. Same species, different populations. So population 1, I got this result. Population 2, I got this result. Let's say I got 1,154 males and 1,780 females. Okay? So now the question might be, well, is there a difference between these two populations in terms of their gender ratio? Let's say I have a third population. We could even do this for 3 or 4 populations. So population 3, I got 1,172 and let's say 1,629. And let's do a fourth one just for fun. Population 4, 1,223 versus 1,654. Okay? So I've got 4 populations of insects now. For each one, I've got a categorical set of data, whether they're males or females, and I want to find out, is there a difference between these 4 populations in terms of their gender proportions. To do that, I go into my tables menu under stat, tables, and then go into my chi-square test for association. So this is a test which actually allows me to compare different groups, much like I would compare different groups with a t-test or a one-way ANOVA. Okay, I'm comparing different groups in terms of the proportions for the categorical variable. Okay, chi-square test for association. It's asking me, how do I have my data? Do I have raw data, which is very rare? Typically, you would have the data summarized in a two-way table. That's exactly what we have. 1, 2, rows and columns, a two-way table. So we're going to select that, summarize in a two-way table, and it's asking me where are the columns containing this table. And I'm going to say to it, these 4 columns, 2, 3, 4, and 5 are the 4 columns. That's all I need, those 4 columns. Click OK, and boom, it produces a nice chi-square test for me. Again, producing a p-value at the end, and it says a Pearson chi-square and a likelihood ratio chi-square, and you can see they more or less give the same result. So it's up to you which one you pick. Typically, Pearson's chi-square is more commonly used, and you can see here the p-value is 0.034. So, is that below our critical p-value of 0.05? Yes, it is. That means we reject the null hypothesis, which in this case is there is no difference between the 4 populations in terms of the gender proportions. In this case, it means there is a difference. Okay? In at least one of the populations, there are significantly more males or females than males and less females, or other way around, than in the other three populations. Okay? So, just like an ANOVA, one-way ANOVA, it's telling us, is there a difference between these four populations? What it's not telling us, just like with a one-way ANOVA, is where that difference is. Is it that population 1 is different from population 2? Is it that population 3 is different from population 1? We don't know. So, again, ideally, we'd like to have some kind of post hoc test where we could compare each population against the others to see where is the actual difference. And again, there's ways of doing that, but those go a bit beyond the scope of this tutorial. All I'll say is what you could do is do individual chi-square tests between population 1 and population 2, population 1 and population 3, which is a lot of work. It takes a while, so I'm not going to do it here. And there's also an error associated with that. Again, there's an issue with doing that might skew your results somewhat. So if you're interested in that, you can look into it, but it goes a bit beyond what you need to know, I think, for this tutorial. Okay, that's chi-square tests in a nutshell. The tricky thing with chi-square tests is to identify when they are useful. And they are useful when you're dealing with categorical data that fall into discrete categories that cannot be measured on a continuous scale. Okay? So that's things like nominal categories, color, shape, things like categories, like even if you measure something. Imagine you measured something like how much people enjoy ice cream on a scale of 1 to 5. You might think to yourself, well, scales 1 to 5, those are 5 discrete categories, right? 1 to 5. That's not something I can measure on a continuous scale, on down to the millimeter or whatever. These are things that fit into categories, and I might have to use a chi-square test to see if there's a difference between two groups and whether or not, and how much they like ice cream. So hopefully that gives you an idea of the chi-square tests. In the next and last tutorial video, we'll talk about correlation and regression analysis in Minitab.